Okay, so I think we've got all of the groups worked out. As I think I had the last wrinkle to sort of deal with this morning, but I think that's all been set. So I think about everybody's formed their final project groups, so that's great. So now you have to sort of start working with your team, picking a system that you like to model, and then submitting in place of a lab report for this week, this input modeling report, which we do the same day as a normal lab report. There's some formatting things and instructions online. If you would like in-person assistance during the lab time, then confirm with your lab TA Shin if he'll be available. Otherwise, you don't have to come to lab for that time. And you can gather data anytime. I just wanted to make sure you didn't have a lab to worry about this week while you're worried about this input modeling report. So the idea here is in a short kind of report proposal, you tell me what system that you've picked out, what's the sort of major problem in that system, like long lines or some other potential inefficiency. There's the reason why you're choosing the system. Tell me the kind of key variables that you think you're going to have to model, and then show me that you have access to the system by going out and in one of those, one or two of those input models or inputs that you've picked out, gather some data. It doesn't have to be all the data you'll use, but gather some data and do the same things you did back in Lab 8, where you can show me that you can fit some input models to it. Do not fit input models to outputs. So don't take Q waiting times and fit input models to those, because you'll not ever use those input models. But like inter-arrival times, demand distributions, those sorts of things, those are the things you want to fit input models to. Again, you don't have to fit all of your input models, but I just want you to demonstrate that you've picked a system, that there's sort of an interesting question driving that choice, and that you have access to that system and can take data on it and can start with actually getting input models that you could put into Arena. There was a question earlier about how complex does the system sort of have to be? You want to be able to justify why you're using simulation, but it is a half semester project, so you don't want to be too ambitious. So it might be that the as-is system that you're modeling could actually be well described by a simple queuing network that you could use other methods like from 470 to analyze, and you don't need simulation for that. But maybe an intervention, like you're going to change things up. You're going to reorder how things come into the system. You're going to change how resources are distributed, those sorts of things that might be harder to sort of understand the effect on the back of an envelope calculation. So that's why you kind of need simulation. So you're not building the sim to just describe a process that you already kind of know the answer to. You want to pick something that you really say, like, I don't know whether making this change would result in a positive effect or a negative effect, and so I need to simulate it. Or something else that you're a question that really can't be answered unless you went ahead and did the sim. So that's kind of what you're targeting there. But also keep in mind that you only have about half a semester to do it. So nothing too complex, keep it kind of narrowly scoped, but still complex enough that it makes sense that you're using sim and not some other tool. And then next week, we'll have Lab 9, where you'll learn about the output analyzer. So we've looked at the input analyzer, the output analyzer, and the process analyzer help us actually compare the output, so we can say that the as-is system is better or worse than the proposed system. And then Lab 10 introduce a couple other advanced topics like batching. Lab 10 is going to be have a significant bonus portion to it. So I think most labs are out of 30 points. And Lab 10 is out of 30 points, but you can score 50 points. So it's almost like you can score another lab on it if you did the whole lab. So if you just want to do just the main part of Lab 10, that's fine. If you want to do all of it to score a couple of bonus points to add on to the labs, then that's fine too. So that's what's coming up there. And then after that, you've got a couple of open weeks that you can keep working on your final project or arranging to having help during that time. So that's kind of the schedule moving forward for labs and practical stuff. This is just summarizing, again, just archiving it here, that the input modeling port is your next assignment here. Due Sunday, like a lab report, it's a group submission. So only one of those in your group has to submit it. I will review all of the input modeling reports and be able to say, like, this is too ambitious, and maybe you have to add a little bit more to this, and those, and so et cetera, et cetera. Make sure that it's okay that you don't have to capture data for all of your inputs, but don't, if you do capture data for outputs, which is great for validation, don't fit input models to them. So it doesn't make sense to like fit a Weibull distribution to a bunch of waiting time data, because waiting time data are outputs. You wouldn't use that Weibull distribution for anything. So just really want to drive that home, that inputs are different than outputs. Details about the desired format and content are on Canvas, so take a look at that. And I put some sample input modeling reports on Canvas so you can take a look at too. Okay, other assignments, ICAs, there's this homework that's been posted. Then after that, there's only one more homework. It's an arena-based homework. So I think that's pretty much it. So any questions about what's due, what's expected? Questions online? Let me open up the other question app here. And I'll probably send out an announcement about this too, but hopefully it won't happen. But if for some reason there are certain individuals on your team that just are not responsive, then I generally, whenever possible, I want groups to handle these things internally. But if there's somebody who really hasn't done anything, that are just sort of on your team in name only, it's okay to leave their name off of any thing that you turn in, and that will then flag it that I need to do further investigation myself to see what's going on, so that that person may have to receive less credit than everyone else. And so Canvas doesn't provide me a great mechanism for people to kind of grade each other, to sort of say like who did what and then rescale things and all that. It'd be great if it did, but Canvas is really limited. So the best thing I can do is say, if you want to flag to me that somebody really wasn't there, even though they sort of planned to be there, leave their name off of the report or like the input modeling report, and then I'll further investigate, and then from there decide if I need to break up the grade somehow. All right, so with that, any other questions, online or otherwise? Okay, so with that, just to kind of get us back into the swing of things, let's start with a quick attendance exercise. So I've got the question written up here on the slide. I'm sorry, was there a question? If yeah, I mean, part of this, I think that goes along with kind of working things out. Like if somebody is sick to the point where they can't do the work, they should reach out to me if whenever they're well, to say, hey, I've been in the hospital or whatever, and I couldn't participate, and that should be something between me and that person. If there's other, I mean, otherwise, you know, I'm sure there are special cases. That's why I kind of want every group to kind of work out their special cases. But if it does look like a group member has not done their due diligence and you're not comfortable with them getting that, then you can leave their name off, and then I'll do further investigation. All right, so quick attendance exercise here. This is kind of, you know, pivoting off of where we left last time. So, I've got these two blanks here, which are filled in by A, B, C, or D. So I've got here that I should be most suspicious of blank p-values when I have blank number of samples. And there could be multiple answers here. So go ahead and submit either A, B, C, or D, or a combination of those, like A and B or C and D. And then we can sort of see what we remember from last time. So I'll put in the chat here, the attendance exercise as well. Okay, so I'm fine sort of just now that we've all kind of submitted, remember, not graded for correctness. I'm actually would love to see your honest answers when I review these things, but we can still talk about it for the sake of the class. So if I look at this, if I sort of go down here and see how many people agree with each one of these, how many people would agree with A, most suspicious of low p-values when I have a small number of samples? All right, so not a whole lot of support here. Any support in the chat? Okay. Yeah. I mean of the person using the p-value to advance whatever their rhetorical agenda is. So if somebody uses a low p-value to state something, then low p-values can mean something, but when do they have the least amount of meaning? So that's really what I'm saying. When do low p-values have the least amount of meaning? When do high p-values have the least amount of meaning? So there wasn't a whole lot of support for low small. What about high large? I should be most suspicious of high p-values when I have a large number of samples. Not a lot of support in class for that. Not a lot of support online. All right, what about low large? I should be most suspicious of low p-values when I have a large number of samples. See sort of a couple of hands coming up in class. And then high small. I should be most suspicious of high p-values when I have a small number of samples. I see some hands coming up there too. So not a lot of support in the class, but in the kind of histogram of things here, then I think there were the most support for C and D, and that's what I would choose as well. So if you have a low p-value, like p point is 0.00000, like 26 zeros, 1, then that low p-value would normally tell you should reject a hypothesis. But if it was coupled with a very, very large sample size, then a very, very large sample size will reject every hypothesis because all models are wrong. All hypotheses are wrong, but some are useful. And so you will eventually be able to reject every hypothesis with a large enough sample size. So if the p-value is really low, but the sample size is really, really large, then maybe you need to rethink what it means for your rejecting that hypothesis. Similarly, if you have high p-values, you might view that as maybe some agreement with the null hypothesis, that may be a reason not to reject the null. But if you have a small number of samples, then that might just mean that you don't have enough evidence to really say either way. So in the coin toss example, if you only have flipped the coin once, you're not going to be able to tell if it's a fair coin or not. If you flip it twice, it really doesn't help you much better. Once you flip it 1,000 times, then you've got enough that it really better be roughly 500 heads and 500 are tails. And if you see a significant deviation when you've done it, when you see an absence of a deviation with a high number of samples, then that high p-value might be meaningful. But for a small number of samples, a high p-value might just mean you don't have enough evidence to say either way. In other words, every hypothesis will have a high p-value for small samples. So any questions on that? I want you to really start, get a conceptual model of p-values that makes C and D super obvious over time. Okay, great. Questions online? All right, back to skim. Okay, so we'll not do this as a attendance exercise, but we'll just sort of do this in class here. So a statistical test with, a test with higher statistical blank will reject a false hypothesis with fewer samples. What word am I looking for there? Anybody online want to put it in the chat, or anybody in class remember the word that we look for? Power is what I'm looking for. Statistical power. A test with higher statistical power will reject a false hypothesis with fewer samples. The Kolmogorov-Smirnov test has higher power than the Chi-squared test. So because of that, if we have few numbers of samples and we're trying to test for uniformity, if the KS test doesn't reject uniformity, we might actually believe it. But if the Chi-squared test doesn't reject uniformity, that's probably just because there's a small number of samples. So higher power means you can detect a deviation with fewer numbers of samples. Now, the flip side of that is once you have a large number of samples, the KS test will pretty much always reject every hypothesis. So once you have a large number of samples, we can't really use a Kolmogorov-Smirnov test because it's so sensitive that it's like if it's not the ideal, it's going to reject it. So it's the flip side of statistical power. So pulling all those things together, we know that I mentioned briefly, we're going to talk about positive versus negative. What's a false positive? What's a false negative? A positive, conventionally, is a detection of a deviation from the null. So you assert a null that might be true. A positive is detecting that it is false, is detecting that it is not the null. So the null might be that a noise you hear is just a normal noise that you'd hear in the workings of a building. A positive would be detecting that, oh, actually that was an abnormal noise. It's detecting the abnormality. It's detecting the thing that isn't the null. So that's what we mean by positive. It's a little bit weird that a rejection of a null is a positive. We want to reject a null. We want to detect a deviation from the norm, and that's why it's a positive. So this alpha is the probability of rejecting a true hypothesis. So if the null is true, what's the probability that we'll reject it? So we can think of the null as a false positive rate, or an FPR. We also call it a type 1 error rate or a significance level. And like we talked about last time, when it's 0, we reject everything. When it's 1, we reject nothing. When it's 0, you're going to have high critical values in most tests. When it's 1, you're going to have low critical values or 0 critical values in most tests. So our p-value is the probability of the observed deviation if we assume the hypothesis is true. So if we assume that the building is operating normally, what's the probability that we would hear a certain creak from the building, and or an even weirder creak from that building? And so that's what gives us our p-value. So we can use that p-value with alpha as a threshold for just making a decision. So if we choose, we're effectively, by choosing alpha, we're effectively choosing what probability we're okay with in making the wrong decision and in detecting that something's. So if we hear a noise that would only occur 5% of the time, or a worse than noise than that, would only occur 5% of the time, then we're saying that we're okay being wrong 5% of the time. That's because that's what's going to happen. It's like if we know ahead of time that a noise like that would only happen 5% of the time under normal situations, if we flag that as a positive result, as a detected difference, then what we're saying is that we necessarily are on 100 goes of this test, 5 of them we're going to freak out when we shouldn't, but 95 of them we're going to get it right. And so that's what this threshold sets, is how big of a deviation is too big for us to ignore. And we just quantify that one way by using alpha, and other ways by using critical values. So that's what we're kind of saying here. So any questions about this kind of stats review, false positive rates, and so on? The idea that a rejection of a null is positive in this class. Okay. All right, so saying that a null is false is equivalent to saying an alternative is true. So that can get confusing when we start talking about positives and negatives. And so a positive result is detecting that a null is false, but that can be equivalent to sort of finding enough evidence to support an alternative hypothesis. And so it gets a little funny that a positive result is, depending on if you're null focused, it's detecting a false. If you're alternative focused, it's sort of like detecting a true. And so it gets a little tricky, but that's why we really want to try to be very explicit about what our null is, and that we're rejecting a null, or looking for detecting a deviation from a null. Now, the other half of this is statistical power, which is just 1 minus the type 2 error rate. So given that our hypothesis is false, So here's our type 2 error up here. Given that our hypothesis is false, the type 2 error is our failure to detect a deviation from the null. So this is like, there really is something wrong in the building, but the noise I hear is so similar to noises I would normally hear. And so that would be a type 2 error. Statistical power is just 1 minus that. So again, we could just write that as, given the hypothesis is false, what's the probability that we'll reject the hypothesis? And so if you have high statistical power, then that means that you will very easily detect deviations from the null. So a test with high statistical power, if it doesn't reject, then that's gives you a lot of confidence that the null is probably true. So a KS test has high power. So when it doesn't reject a distribution, we have a lot more confidence that distribution's actually the real distribution. But a chi-squared test does not have a whole lot of power, for a given sample size. So if a chi-squared test fails to reject, it doesn't really give us much evidence of anything. So that's what we mean by statistical power. So that's also why sometimes it's known as sensitivity or true positive rate. So a test power is modulated by how variable the data is and how many samples that you've taken. So we're going to do power analysis in part 2 of your homework. And that power analysis helps you determine either how big of a sample size you need, or for a given sample size, how small of a difference can be detected without taking another sample. So any questions about these terms, power and its relationship to type 2, or any of the rest of this? Questions online? Okay. So very often when we build hypothesis tests, we form what's called an ROC curve, a receiver operating characteristic curve. This is something that if you go into a data science course, you take some machine learning, you'll definitely see these. And so what we plot here is we have a given hypothesis test. So in this case, these are 3 different classifiers. So you can think of these as 3 different hypothesis tests. You can think of it like as Chi-squared and Kolmogorov Smirnov and I don't know, a t-test or something like that. So there's 3 different classifiers that can bin things into one group or another. And so each one of them has a type 1 error rate and has a statistical power. And so if you swing that alpha on each one of these tests from 0 to 1, you're just changing, so normally we would fix ours at 0.05 down here. But if you let it get bigger, what you're going to do by increasing the false positive rate is you're also going to increase the statistical power. And so the strength of a test is how far away this curve for each one of these tests gets from a diagonal. Because what the diagonal is how good of a classifier of coin is that's weighted with alpha as its probability of coming up heads. So if you flip it, you could say, I heard a weird noise. Is that noise too weird for me to withstand that I need to go out and check it out? You could flip a coin and say, this coin comes up heads 75% of the time. And whenever it comes up heads, then I go out and I check out the noise. That alpha right there, that's like the weightedness of the coin. So if it comes up heads 5% of the time, then I flip a coin and it's only going to come up heads 5% of the time, and I'm going to go out the door 5% of the time. That is a way I can ensure that I will definitely have a type 1 error rate of alpha just by flipping a coin. But it, of course, isn't at all related to the data. And so my statistical power will also will fall along this line. So it's kind of the null hypothesis test, I guess is what I'm saying here, is just flipping a coin at random chance, where the chance that you're going to come up heads is your alpha. And that's what this diagonal line represents here. A good hypothesis test is going to have a bend on it like this, and it's going to have an area in between this diagonal and the actual relationship there. So the best hypothesis test is going to actually look like it'll go straight up and then straight over. And but most hypothesis tests are going to have a curve that looks kind of like this. So the farther they get away from the diagonal line, then the better they are. As you take more samples, you move a hypothesis test toward this corner. It gets more bendy. But for the same number of samples, a hypothesis test that is closer to this corner than this line is better than another hypothesis test. So very often when you're designing hypothesis tests, you compare them by how much area is under this curve in between this line and the diagonal. So I'm putting that up there, not because I'm going to quiz you a whole lot on ROC curves, but I do want you to know that an ROC curve compares error rate versus statistical power. But I'm putting this up there because I want you to see there is a fundamental trade-off that as you give yourself more error rate, which sounds like a bad thing, you're also getting out of it more statistical power. So if you are in an application space where the true positive rate is more important than the false positive rate, then you might give yourself more false positive rate just to buy yourself more true positive rate, and vice versa. So in certain medical applications, their alphas are really, really low. In other applications, the alphas might be high. And it's all navigating this trade-off space. All right, so any questions about that? Whether the term receiver comes from, these curves came out when radar was just becoming a thing, and humans would look at radar screens and they would have to detect whether something was a real thing or like a biological agent or something else. And so some were really good at detecting like planes on radar, but others would constantly keep like detecting birds as planes. And so whenever they'd say, a plane, they'd go out and they'd see, is it a plane or not? And they'd see how often they get it wrong. And so each of these lines would represent effectively a person. You could say like, every person would have a threshold where you could sort of give them a threshold of a sensitivity, which would represent kind of a desired alpha. And as you swung, you asked those people to be more and more discriminating. Then you could sort of see what curve they got here and how far away they are from just flipping a coin. And so these were radar receivers, and that's where this term receiver operating characteristic came from, as a way to pit some radar receivers against another to see which ones were better at balancing these two things. But now we use it to pit hypothesis tests against each other, like the chaos test or the chi-squared test, or application-specific ones like these ones for machine learning. Okay. So any questions on that? Just keep that in mind. I'll show you sort of cartoonized ROC curves kind of throughout most of the rest of the semester. So that's our sort of introduction to where they come from. Okay, so other review stuff here. So average and variance, make sure that when you do sample variance, you do the n-1. Likewise, if you're doing discrete, make sure when you're calculating the average, you multiply by the frequency of each outcome and also the n-1 for the variance. Likewise, if I give you a histogram, pretend like the histogram is discrete, where the midpoint of each bin is the discrete outcome, and then the frequency is how high the histogram is, and you can calculate the average as well as the variance. But again, make sure you use n-1 in the variance whenever you're using the sample mean inside the variance formula. So any questions about those formulas? Hopefully that's review 2. And the n-1 is pretty clear. All right. So we've got these distributions, various distributions, discrete and continuous. And, so we talked about the maximum likelihood way of choosing parameters. So given data, how do we choose the parameters for the distributions? We did this example where I said, well, if I know something is an exponential, or at least want it to be an exponential, and I have a bunch of data, with a little bit of calculus, you can show that the maximum likelihood estimate of the parameter lambda in this exponential is just going to be 1 over the average value of the data that I've gathered. And we can look up in a table a bunch of maximum likelihood estimators for parameters in a range of different, very common distributions. So these are distributions that we've talked about in the class. Here's one we haven't. So Banks has got these in table 9.3. But if you pretty much look up any distribution on Wikipedia or whatever, it will probably give you a column somewhere there. It'll say the maximum likelihood estimator for these parameters is, and they've already done the calculus for you. And so that's what you'd like to do. This is a great way to start with choosing a parameter to put into ARENA. All right, so questions about any of that? Okay. All right, so where we left off last time is didn't get through our new modification of the chi-squared test and the KS to be used on any distribution. The chi-squared modification is probably something that you're familiar with from 380. But the basic idea here is if things are distributed so before we used the chi-squared test for saying, are things uniformly distributed? Now we're saying, are they distributed like some hypothetical distribution? So we're saying if the range of our random variable is partitioned into subintervals, then the expected count of samples in each interval is the total number of samples times the probability that the hypothetical outcome would fall in that interval. And so if I've got a PDF or a PMF for my hypothetical distribution, I can then say, if my interval's from 0 to 0.5, then I can say, well, what's the probability that I get an outcome in that whole interval? And I take that and multiply it by my total number of samples, and that's the expected count that I expect in that bin. So otherwise, it's pretty much going to be the same chi-square that we did from before the midterm. And I'll do an example here in a second, but we have to keep in mind that if the expected count for any of the bins is less than 5, then we have to deal with that. And so we either will need to combine bins to make things higher than 5, or if that's really not feasible to do, use a different test that has higher statistical power, namely, in our case, the Kolmogorov-Smirnov test. And we'll talk about that here in a second. So that's what I'm saying here. So if sample sizes are smaller, we're going to use the KS test. And I'll show an example of how to do this, but at a high level, how do we modify the KS test for any distribution? It's pretty easy. We sort all of our samples just like we did before the midterm. But then we take each one of the samples and we run it through the CDF for our hypothetical distribution. So before the midterm, we only were worried about uniform distributions or between 0 and 1. And so we just looked at the sample itself and said, is the sample itself in this interval? After the midterm, we say whatever the hypothetical distribution is, we take its CDF, we run the sample into that, and the result will be between 0 and 1. So effectively, we're doing a KS test on the uniformity of the CDF, as opposed to the uniformity of the data itself. So if you run the data through its CDF, you should get an approximately uniform distribution that we can test with the KS test. And I'll show an example of that here in a second. So sort the numbers, and the sampling ith position should be in the quantile between these, and that's what we're saying here. So let's see how that all works here. So for the KS test, we're measuring the distance between two CDFs. A one sample test, we call it goodness of fit test. It measures the distance between the empirical sample and our reference CDF. There's also a two sample test, and this is also the same for a chi-squared. And so in a two sample test, if you have a distribution from one population, a distribution from another, and you want to see, did both of these data come from the same distribution? That's a so-called two sample distribution test. And you can either use a k-squared or chi-squared test or a KS test to test for those. And that's not something we do in this class very often, but it's definitely something that I just reviewed a paper last night that did exactly that. So, so that's a very common way to use these as well. It's not just comparing data to a hypothesis, but comparing two data sets to each other you can do with these tests. So KS is particularly good with sample sizes are small, but maybe overly sensitive because of its high power. And it's really only usable when parameters have not been estimated from data. So when you really know the hypothetical mean, you don't calculate the hypothetical mean from data. So So yeah, so how does the KS test look like here? I thought maybe I skipped over them, but I thought I had a chi-squared example. Maybe it'll show up out of order. But if not, I'll just go back to the other slides and make sure I get the chi-squared. So starting with a KS first, if we had a bunch of these data values and we were testing for uniformity, then this is a uniform CDF compared to our empirical CDF, where we just plotted the data values against their rank. This is exactly what we did before the midterm. This is how we use the KS test to test for uniformity. We basically looked at what is the gap between every data point and the CDF that we would expect for a uniform distribution. Now, what we're doing, and so we do that in a table form like this. So we sorted all of our data, and we said, is it in the interval that we expect? And that's exactly what I'm showing graphically down here. Here's our data point. Here's the interval we'd expect it in. Here's the data point. Here's the interval we'd expect it in. Here's the data point. Here's the interval, and so on. So we're measuring the distance between the data points and the expected interval. Okay, great. Now, how do we modify that for any distribution? Well, all I'm going to do is, when I advance to the next slide, is take our data points and pre-process them by running them through the CDF of the hypothetical distribution. So now I've got data points X, and I think they're distributed, or we'd like to test that they're distributed like CDF F. So I'm going to run all of the data points through the CDF, and that's going to give me values between 0 and 1, because CDFs are probabilities. They always have values between 0 and 1. And now I test for the uniformity of these scaled values effectively. So what I'm doing graphically is down here, where I have my hypothetical CDF is this bendy guy here. And the data points after being processed through the CDF are these asterisks. And the expected position of them, if they're consistent with this CDF, is sort of given by these intervals here. And so the idea that I'm kind of looking for here is the first data point, when I run it through the CDF, I'm kind of expecting it to be in the first 20% of the distribution. The second data point, after I run it through the CDF, I'm expecting to kind of be in the second 20%, and so on. So this is exactly the same thing you did before the midterm. The only difference is you run the data through the CDF first, and then do the steps identical to the way you did before the midterm. The same, you look in the back of the book, you look in the same spot to get the critical values, and so on. So that's the KS test for arbitrary distributions. So there are questions about that, about the KS test for arbitrary. If you know how to do it for the uniform, it's identical. Just before you do the uniform part, you take your data and run it through the CDF to generate new values that you then effectively test for uniformity after that transformation. So questions about that? And that's another nice kind of tip, is that if you happen to pick the right CDF, if you take any data and pipe it through its CDF and then histogram the result, you should get something that looks approximately uniform. If it doesn't, then that means that that CDF and those data don't go together. Okay. So the downsides of the KS test, if you have estimated parameters, you really can't use it except for a couple of specific distributions like the normal. So what I mean by estimated parameters is you have to say, I'm testing against an exponential with this mean. I can't say I'm testing with an exponential with the mean of with the sample mean of the data. If you are estimating a parameter from the data, you cannot use the KS to test for that relationship, unless it's very special cases like the normal, the exponential, and the Weibull. But if it's a generic distribution, another distribution, a beta distribution or something like that, and you're estimating parameters from the data, then you can't use the KS test because it needs to be specially tailored for every single time you do an estimated parameter, unlike the chi-squared test, which can be used for estimated parameters. So any questions about that? And then I want to hop over to somehow, when I hacked these slides over, I somehow skipped my chi-square example. So I need to jump back to the last week's slide, or last lecture slides to make sure we get those. All right, so let me jump back to lecture G3. There we go. All right, good. All right, so let me just jump ahead to, let me see if I can find those slides first. Down here, this will do. All right, so jumping back to the slides from last week. All right, so chi-squared test. So this is what I was trying to say here is that when the chi-squared test here, we're going to calculate the same expected chi-squared value. We have observed counts in the bins that you've picked, but now the expected counts have to be, you have to use this formula where, like I said before, is the number of samples times the probability under the null or under the expectation that you get outcomes within the interval that you're looking at here. And so we'll see a more concrete example here in a second. And if you have classes that have an expected number of counts less than 5, you want to combine them with neighboring classes until you get a superclass that has an expected value greater than or equal to 5. And our goal is to use as many classes as possible. So if there's multiple ways you can combine things, try to combine things so that you still end up with the highest number of intervals afterwards. So don't, so if there's an option of combining with the left or combining like, 2 on the left or 1 on the right, well, if you can manage to get away with not eliminating an interval, then go that way, because we want as many intervals as possible to make the chi-squared test work as well as possible. This 5 is a conservative threshold. It's what we use in this class. I think it's what's used in 380 as well, and it's generally common in science. There are special versions of the chi-squared test that allow you to use less than 5, like Gates continuity correction for the chi-square test, and you can look up those sorts of things. But if you're using the plain old vanilla chi-squared test, you should always use 5. And if you can't get 5 in a bin, then you shouldn't use the chi-squared test. You could look for something else like the Kolmogorov-Smirnov test. The critical value is the maximum allowed deviation for a significance level. The other thing that we're modifying from pre-midterm to after midterm is that degrees of freedom, it used to be just the number of classes minus 1. Now it's the number of classes minus 1 minus the number of parameters estimated from data. So if a parameter is part of the hypothesis, it's not estimated. If I say, here's a bunch of data, test to see if it's normally distributed with mean 5 and standard deviation 2, then 5 and 2 were given to you as part of the hypothesis. They're not estimated. They do not penalize the degrees of freedom. But if I instead say, here's a bunch of data, test to see with the chi-squared test if these are normally distributed, then you're going to have to estimate both the mean and the standard deviation from the data, in which case you're going to have to reduce your degrees of freedom by 2. So the total reduction here will be n minus 3. 1, just because it's a chi-squared test, and then the additional 2 because you estimated 2 parameters. So I think I've got some sort of additional justification for that. So we subtract 1 when we do the chi-squared test because basically the chi-squared test breaks up the number of counts into a number of observations that all must add up to the number of counts. So we know that we have 100 counts total, and those 100 counts are distributed up into a bunch of bins. Well, once you know n minus 1 bins and the number of counts, that nth bin you already know. There's no freedom there. So that's why we say a chi-squared has a natural upper limit of n minus 1 degrees of freedom, because you're taking 100 data points and you're smattering up around n bins, so you really only get n minus 1 degrees of freedom and the other bins fixed. So that's the reason why we start with n minus 1 degrees of freedom. Things get worse when you estimate parameters. Because if you estimate a parameter generically like this, so here's a parameter theta hat, estimated with some function with our data. Here it is specifically, if we're estimating the mean, sample mean from our data, then this looks just like this here. So basically, once you know the mean, you've now fixed another degree of freedom. So now if I know the number of data points and the mean, if you give me n-2 data points, I probably can solve for the other two. So I don't have enough of as much flexibility in my data. So it's as if I just deleted 2 of my sample points. So, so this deletes 1 sample point, and this deletes another sample point. So now I'm stuck with n-2 degrees. Every estimated parameter has this effect where it penalizes your degrees of freedom by 1. So once you get down to 0 degrees of freedom, you effectively have just taken your data and loaded them up into the parameters, and you've got no room, and that's what we refer to as overfitting. So, so you always want as high a degrees of freedom as possible. So any questions about that? What I mean by degrees of freedom and why in the chi-squared test, it has this formula where it's always n-1, but then minus the number of estimated parameters. And this affects what critical value you look up in the back of the book. Okay, so examples of that, I've already kind of given one of normally distributed in the mean and standard deviation are estimated, it's n-3. If instead I give you, and I happen to pick the same numbers as I just said, as part of the hypothesis, there's no penalty. So my degrees of freedom are n-1. Now the weird cases are there are certain shape parameters that are not really fixed by the data or don't fix the data. So like a uniform distribution, I might choose parameters A and B based on my data, but knowing the outsides of the ranges doesn't really allow me to solve for any data points. Like it doesn't really fix any of those data. So I retain my degrees of freedom. So these types of parameters, like for triangular distribution in the range, for uniform distribution in the range, don't get penalized. But the mode in a triangular distribution, that is something that does get penalized. And so things that are intimately tied to the data get penalized. Things that are sort of loosely specified by the data don't get penalized. And so this can be a little funny sometimes, but you get kind of the hang of it after a while. All right, so any questions about that? What I mean by estimated parameters and free parameters. Okay, so the example, so this is sort of the example from pre-midterm, give you a bunch of points. I wanted to test to see if it's uniformly distributed, and now we can look at it through the lens of our generic chi-squared distribution. And so we count every, we cut it up into 4 classes. We count how many of these observations land in each one of the 4 classes, and there's our observed numbers there. And then if we, under the uniform hypothesis, the expected value in each bin is going to be equal to the total number of samples times 1 over n, because 1 over little n is the probability that from a uniform distribution that that we would have samples in each one of these bins. And so there's 4 bins, so there's a 25% chance that you land in each one of these bins. And so this is just taking the total number times 25%. Since the total number is 30, 25% of that is 7.5. So that's where we got our expected count. And so that's a generic way of doing it. We confirm that it's greater than 5 or equal, at least 5. So we can continue on with the chi-squared. So then we go and we fill this in. Now, here, we're only going to use a degree of freedom of n-1 - 0 because we haven't estimated any parameters from data. So we calculate our degree of freedom as being 3. We have our alpha of 0.05. Since this is since chi-squared is an always positive statistic, this is a one-tail thing, so we can use the 0.05, not 0.025, and then we get the 7.81 as our critical value, and that's exactly what we did before the midterm. We just left out the details of this n times probability stuff. So how do we calculate the expected value for an arbitrary distribution? Well, it's not too bad. So for a discrete distribution, you just sort of say how many outcomes would be in this interval and add up the probabilities of each one of those outcomes. So if your interval is from 0 to 0.5, and you've got a 0.25 outcome and a 0.4 outcome, see the probability of both of those, add them together, and that's the probability of landing in this bin from 0 to 0.5. If it's a continuous random variable, you'll have to integrate under the curve. So you have to integrate from 0 to 0.5 under the density function. But so for any interval, it's going to look like this. But if I give you the CDF, then it's just going to be the CDF evaluated at B minus the CDF evaluated at A. And that's what we've got here. So in general, for the continuous distributions we worry about in this class, this upper formula is pretty much all we need. Or in other words, right here, this formula here. So if I give you the CDF and you need to do a chi-squared, you do not need to do any integration. You just plug in the upper limit of each interval minus the lower limit of each interval, and that will give you the probability of it landing in the interval. Then you scale it by the number of samples, and that's your expected number that goes in that bin. All right, so, and this is just demonstrating that. So here's an exponential, and that's, the bin is from 2 to 3, so I can do the CDF at 3 minus the CDF at 2, and I get that probability, multiply it by my number of observations, and that gives me the expected number for an exponential in that range. So any questions about the chi-squared and how we've generalized it to any distribution we want, not just the uniform? Questions online? Okay. All right, I wanted to make sure we got through those. Those will definitely be important for the homework in particular, because you'll be doing a chi-squared. Let's hop back and cover a couple of other little things then for this lecture. If I can find, there we go. Okay. Shoot. All right. So let me just head to the point we left off here. All right, so last couple of things you should, we're not going to work a lot with the Anderson-Darling test in this class, but it's a little bit more modern way to work on these distributions. And so you'll see that, you know, when it's similar in principle to the KS test, but it allows you to sort of amplify where it is looking or where it is kind of testing for it allows you to penalize different parts of the distribution differently. So it's a very flexible and very powerful test. And so this is one of those options where if the chi-squared test isn't working for you, Anderson-Darling's a good one. The other thing you need to do is we'll learn that a lot of the tests we have to use in this class require distributions to be normally distributed before you can even use a test. Like I can't use a t-test unless I'm sure that the data I'm using the t-test on come from a normal distribution. So technically, before you do any t-test or any generalized linear model, so an ANOVA or any, I mean, there's just a bunch of different examples, I'm gonna have to test for normality. So the Shapiro-Wilk test is a distribution test specific for normality that says extremely high power. So, so this is one, again, I'm not gonna beat up on you in this class, but when you leave this class, if you try to ever do a t-test or an ANOVA or a generalized linear model of any sort, then someone in the kind of chain of custody of your report is going to expect that you have checked for normality before you ever did that test. And you can do that by doing a Shapiro-Wilk test. And all modern statistical packages will have a Shapiro-Wilk test. It has high statistical power, which means if you have only a few number of samples, it will be able to detect a deviation from normality. And so if you say, I've got 10 data points, are these normal or not? If the Shapiro-Wilk says that it doesn't reject normality, and you've done a QQ plot, and the QQ plot looks like they're pretty normal too, you can be pretty confident that those data are going to meet the assumptions of a t-test, of an ANOVA, of your linear model, or whatever. But you have to do the Shapiro-Wilk test kind of first. So again, I don't want to, it's too much for me to beat up on you on this in this class, but I at least need to introduce it, because if you leave this class and you start doing t-tests and related, you really need to be doing the Shapiro-Wilk first. All right, so, and it is just a distributional test only for normality. You can only use it for normality. All right, so that's kind of the big things about goodness of fit. I'm not going to kind of spend examples from lecture G3, but we kind of already covered this already. I do want to mention, since I just said it, don't forget about those QQ plots. Great thing for your input modeling reports as well. Couple any quantitative analysis with a graphical assessment of the fit as well, because people usually don't trust one or the other, but you compare them both. And if you say, I've got a distributional test that didn't reject, and hey, look at a good graphical fit. This is not a good graphical fit. This would be, I'd say this one here is probably not going to be very convincing, because it's kind of off the line here quite a bit. So if it is on the line and it's not rejected by a rigorous statistical test, then I'm pretty sure that you've got the right input model. So don't forget about your probability plot. They're super helpful. And then you've already gone through Lab 8. I just want to highlight in Lab 8 that the input analyzer gives you, it's kind of blurry in class here, but it does give you the distribution and best fitting parameters and the expressions that you can dump into ARENA. It gives you a measure of error. So that error, that squared error, you want that to be low. And then it gives you two tests. It gives you the chi-squared test as well as the KS test. If you have a lot of data points, it doesn't even bother the KS test, because all KS tests will be rejected with a lot of data points. Gives you the summary statistics, mean, etc., and it gives you the details about your histogram, how many bins, and so on. So all of these things are just text. Do not, in your input modeling reports, give me screenshots of this stuff. Like, this is a terrible histogram. You can generate a better histogram on your own. You know how to do it. So generate histograms on your own. And then if there's data out of here, just report it in the text or create your own table. You don't have to give me all of this. All of this probably isn't relevant to the argument you're making. This is just meant to be a quick way for the input analyzer to show you data that it thinks you might need. But don't take a screenshot of this whole thing and then say figure one, see figure one, and then let me parse it out. Show me that you know how to read this. Generate your own histogram in Excel, and then generate data, or then pull the numbers out of this. You don't have to do your own chi-squared test or your own KS test if it's done it for you. But if you only care about the chi-squared result, then give me the chi-squared results out of this table just by typing them out or putting them in a table. Don't give me just a screenshot of this little ugly text that the input analyzer put up together. And yeah, so this is just sort of tips, but you guys have already gone through Lab 8. So you kind of know all of those. But the other thing to point out is that the chi-squared test, like in this particular example, it's hard to read on the projection, but it has a p-value of like 0.6, so not rejected. But the KS test here has a p-value that's really small, 0.03. And so the KS test here actually rejects this, and I thought it's hypothetical distribution, which I think is a triangular distribution. I don't have any screens that have a nice enough resolution up here to see that. But the idea here is that visually that looks like it could be a triangular distribution. The chi-squared doesn't see any problem with that, but there's so much data, lots of data, that the KS test, these little deviations are enough to trigger the KS test. And so if you were to say, oh, that's not triangular to me because the KS test rejected it, you know, I'd say, oh, you're probably being like overly sensitive. How triangular do you need it to be? And to me, I'd say for probably simulation purposes, if you put in a triangular distribution into ARENA, you would reproduce all of the salient features of these data. So again, if you have high levels of data, be careful about really sensitive hypothesis tests because they're almost always will reject. Okay. So any questions of that? All right. So we're probably going to have to cover some of this the next time, but we'll eventually catch up. You know, but the big thing here is we're moving kind of from input modeling to verification and validation. And so now we've hopefully picked good inputs, but now our question is, now can we look at the outputs and compare the outputs to real world outputs to see if there's something wrong in either our fundamental structures here or something that we didn't detect that was wrong with our input models. And so that's what we're kind of being big in here is we want to test completed simulation. We want to verify that there's no coding errors. So verification means basically debugging. And we want to validate that our model structure and assumptions are correct. And so we are using testing to verify there's no bugs and to validate that our model actually makes sense relative to the real world. So that's what we mean by tv&v, testing, verification, and validation. And so we've got kind of this flow chart here where you've got your real system. You need to sort of verify conceptually whether you've got all the right components. This is kind of like what you're putting into your input modeling report. These are the components we think are important. You're going to build a computerized model of it. And then from that computerized model, compare it to the real system. And if that comparison is really off, then you either need to adjust parameters or you need to add maybe whole new structures or take away whole new structures from the computer simulation. And so this process here of this iterative process of updating the sim is what we often call calibration. So calibrate is increasing the caliber of your simulation. It's where the term comes from. And we start with initial value model, compare to reality, have a revision compared to reality, and so on. There's always room for further calibration, but eventually we stop when things are good enough. And so, so that's what we mean by these terms. So verification is debugging, validation is comparing our idea of what the model should be to what the real world is. And then calibration is the iterative process of making the model closer and closer and closer to reality. So this is V&V and calibration. So TV and V and calibration all kind of go together. So just some definitional things. All right, so this is an example that I'll maybe start here for a couple of minutes and then we'll pick up with next time, where we're going to get an opportunity to use some statistical tests and a power analysis that get us closer to what you're doing in part 2 of the homework. So the setup here that we'll pick up on next time is we're modeling a bank. So this is a drive-through with a bunch of bank tellers here. There is an inside of the bank as well, but we're focusing just on the drive-through. So the idea here is that this is the type of variables I would expect you to have in your input modeling report. Like you said, I want to study a bank. This particular bank has huge queues at this time of day. When I want to study this bank, I think it's important for me to model the arrival rate to the bank, how long it takes to serve each type of service call. So maybe they need to deposit a check, that'll take a certain amount of time. Maybe they'll need to do something else, that'll take another amount of time. And so I've got all these service times. Those are our random variables. Those are the things that we'll need input models for. I've got decision variables, which are the things that I actually can control as an operations researcher. How many tellers are in the bank? What's the average service time? How many lines there are? Those aren't things that those are things I might measure to know what the current state is, but those are the things that I'm going to tweak inside my sim to try to make for a better bank. And then I've got outputs, how utilized the tellers are, What's the average delay for each customer? What's the longest line of the queue? And so kind of summarizing those things, we only build input models for these things. So when you're writing your input modeling report, this week, then when you're trying to fit input models, don't try to fit I don't want to see models fit to any of these things. I only want to see models fit to things that fit into these inputs over here. So those are input models there. And so these will be measured when we run the sim, and you should gather data on these from your real system, but you're going to compare the real system to those after the system is built. So you don't need a model of those, because we're going to compare in a 2-sample test these data to the simulated data, or rather the real data to these simulated data. So we're going to compare those together. So we've got our inputs, our model, and our outputs. Do not fit anything to outputs, only fit to inputs, and so on. So I'm going to stop there before we get into the quantitative stuff. We'll pick up where we left, or pick up here next time. Let me just jump back to a final attendance exercise. And get my mouse back. There we go. And the question I have here is, what is the probability distribution that the Shapiro Wilk test tests for? So what probability distribution is associated with the Shapiro Wilk test? And again, not looking for correctness, just looking for coherence and completion. So, and that's all I've got for you. So if you have any questions, feel free to come up. Otherwise, we'll see you on Thursday for, I believe, a Halloween themed lecture. Any questions online? If not, then I'll go ahead and close the room.